to another It's Not Quantum Physics. We're going to continue with the A-level content that we've been working through. Today we're going to talk about sine waves and how they relate to circular motion. So here is the content that we need to cover regarding what the exam board has talked about. And so far we've dealt with conditions for SHM and defining that equation. We're going to explain why omega squared is our constant of proportionality, and also we're going to define this idea of displacement being related to cosine or sine of the angular velocity multiplied by the time. Right, okay, so we're going to start by thinking about what we had last lesson, which was this idea that if we've got a pendulum and we've got a turntable with something on it, then the shadows of both of those are going to match. Okay, so as that object moves round, the shadow will move backwards and forwards in the same way that the pendulum will move backwards and forwards. So we're linking, the whole idea about this is linking circular motion with simple harmonic motion. That's what we're aiming to do, and we've sort of done that already, but we're going to use that a little bit more in this lesson. Now, it's not a huge amount of theory to go through. There's a bit of maths that we'll do, and as always, if there's anything you don't understand, just sort of stop me and we can go through it. So we're saying that the pendulum can in fact be mapped onto circular motion, and in fact I'm going to go a step further and I'm going to say that can in fact be mapped onto a spring system as well, because that also follows simple harmonic motion. So all three of those can all be mapped together. Now let's take, for example, our situation we've got here. We've got Q and we've got P. And let's start with P, because starting with this object that's on the turntable that's rotating round should be relatively straightforward for us now, because we have worked through the circular motion content and we know what's going on. We know that in order for P to carry on rotating round in a circle, there must be a force acting towards the centre. We know that the value of P has got, that P itself has got a velocity that is tangential to the rotation that it's taking, and the reason that velocity is able to keep changing is because we have this force, and so we have this acceleration. So acceleration then is equal to the negative velocity squared over the radius, which we learnt in the previous topic. You know, there's nothing new here, hopefully, from what we're talking about. Now, I've realised that actually that diagram's a bit complicated, so let's just simplify it for a second. Here is our object that's moving, and we'll put in our pendulum as well, so you can see what we're talking about, and they're both acting at the same point. So let's use the same colours. We have the force, the centripetal force that's pulling P inwards, which means that P will keep going round in a circle. We know that P has a tangential velocity that's going to change each time, and because we have both of those things, then P will move round in a circle. So that is a top-down look at P and Q. And we know that Q is also going to move in that way. I'll kind of put it in the centre. It's going to move in that way, and P will move around. So it's going to rotate round that disk. It depends upon how we're looking at the shadows as to what's going to happen. So we know that acceleration is v squared over r, but we also know that the velocity is omega r, where omega is 2 pi f. We'll just remind ourselves that as well, because that's quite important for us to work with. Okay. So that means we can actually redefine acceleration. So therefore, acceleration, if it's minus omega squared over r, then that's the same as saying if it's minus v squared over r, I'm getting ahead of myself, then that's the same as saying minus omega r all squared over r, which is going to be minus omega squared r squared over r, which is minus omega squared r. Okay, so we know the acceleration and what is happening to p as it's going round that circle. The acceleration towards the centre is going to be, well, the acceleration in the opposite direction, because remember it's going to act towards the centre, is going to be minus omega squared r, and hence where the minus comes from. Okay, so that talks about p. Let's now try and map that so that it works with q. And I'm going to just rub these bits out again, because we'll do some more bits down the centre. But we're going to consider a bigger diagram of what's happening. I'm going to place P over in this position here. It's right on the edge of our turntable that's rotating. And we'll define the centre point. So that means that we can say that distance there is r. We also know that that distance there is r. But using our trigonometry, we can actually define a horizontal and vertical component. And these horizontal and vertical components are going to be important when we consider the fact that we're projecting the shadow onto the screen. So here is my light. And my light is going to hit my hit the ball here, hit P here, and as P is moving round, then there is going to be a small shadow behind it, and we're going to be talking about where that shadow is in relation to this 0 point here. Because remember that 0 is going to be the centre. That is its point of equilibrium. If it was a swinging pendulum, that's where it would want to be at rest. So in this case, we're going to define our distances relative to the centre. Well, we know this angle theta, and this angle theta is how far round the circle we've gone. So in which case, we can zoom in to what we've got here. Using our centre point, and this time actually I'm going to put dashed lines in. There's the ball at the end, so there is our point P. We know that value is r. We know that value is theta. So therefore we can say the one that's opposite is going to be r sine theta, and the one that's adjacent is going to be r cosine theta. So our displacement in this x direction, and we're going to classify this as the x direction. And you could do the same in the y direction, but it doesn't matter for us right now. It really doesn't, it's not going to make any difference. It kind of comes in at degree level. But in the x direction, the displacement of this shadow, as the ball is moving around the turntable with the light shining upon it, is going to be related to r cosine theta. Which also means we can define the acceleration relative to the x direction. So our acceleration in the x direction, so a subscript x, is going to be our acceleration multiplied by our cosine theta. It's going to be still in the same manner that we've got our displacement. So therefore we can say that our acceleration of the ball's shadow, so of P's shadow, because that's really what we're talking about here, is going to be AX. So we're talking about the x direction. Now we're using the fact we know what A is from the previous bit of work we did. So we said that A was minus omega squared R. So therefore we can say that A is minus omega squared R. And we've still got our component, because obviously it depends upon where in the circle we are as to how much of that acceleration is going to act in those directions. So a subscript x, the acceleration in the x direction of P's shadow is minus omega squared r cosine theta, and that is because, remember, we've just said previously, and I'll write it again here, the acceleration is equal to minus omega squared r. So all I've done is put that into our equation here. So that's quite an important equation. But we've still got an r cosine theta. Well, that's quite nice, because we've now said that r cosine theta is our displacement in the x direction. So therefore, we can actually say that the acceleration in the x direction is equal to minus omega squared, and this r cosine theta is going to become x. Where, and we'll add a little caveat here, so where x is equal to r cosine theta, and that comes from this part here. So it comes from the fact that we've got a proportion of our displacement in the x direction as being r cosine theta related to how far around the circle we've gone. So x is equal to r cosine theta. We're now back at acceleration in the x direction is minus omega squared x. Well, hang on, because last lesson, didn't we get to this idea that acceleration was proportional to the negative displacement? So we said that acceleration was proportional to the negative displacement, and then we said that the constant of proportionality, and I said I wasn't going to explain it in that lesson, but the constant of proportionality was was omega squared. Well, we just proved it there. So the fact we've ended up with ax, and I will write it again because I think it is quite important, is equal to minus omega squared r cosine theta, then we can also say, obviously, that that is minus omega squared x, so therefore that is my constant of proportionality. So it's all related to the frequency of our object that is moving. Okay, so let's now try and tie things together. So as this pendulum bob Q has the same movement in the x direction as P, then we can also say that Q has an acceleration in the x direction of minus omega squared x. So that brings us back to what we talked about last time, where we said that, and I'm going to do it once more because I think it's important, acceleration is proportional to minus x, minus displacement. So acceleration then is equal to minus kx, and we've just said it's minus omega squared x, so therefore we can say minus omega squared x is equal to minus kx, so we can say that k is equal to omega squared. So it's that proof as to where that comes from. Okay, so that is how we're getting to this idea of acceleration being proportional to minus the displacement, and actually the proportionality being the angular velocity. No, am I right there? I have to think. But being omega squared. Let's get those right in my head. Okay, so now let's relate it to a sine curve, because we know what this displacement looks like at every stage in a situation, in a simulation, in a simple harmonic motion. So we could start. Let's look at two situations where we've got an object oscillating with a frequency of f. we could say we know that A is equal to minus omega squared x. That's fundamental for simple harmonic motion. And we know what omega is. It's 2 pi f. But what does x depend upon? What does this value x depend upon? Well, it depends upon where we start our oscillation from. If we start it from the maximum amplitude in one direction, then we know what's going to happen next. It's going to swing the other way. If we start it from 0, then if it's not had a push or it's not been moved, then it's going to stay at 0. If we start it from negative maximum, it's going to start oscillating back the other way. And if we start it from any point in between, we actually know that it's going to follow that sine curve, because that's what we learnt in the lesson, in last lesson, where we looked at the graphs that go with it. So x is dependent on the start position. So if at t equals 0, x is going to start at 0, so it's going to start at the midpoint, then our graph will have a maximum amplitude, we'll have a minimum amplitude, we'll have a 0, but we know it'll start from 0, it'll go to the maximum, come back to 0, it'll go to the minimum, come back to 0, go to the maximum, and so on. We'll do one more. And we can see we've got a sine curve. So our solution for x is going to be sine lots of my omega multiplied by the time, but the maximum it's going to reach is my amplitude. So our solution to this situation where it starts at 0 is going to be a sine omega t. What about if it starts at a maximum amplitude? Well, if it starts at a maximum amplitude, hopefully you can already see this, we're going to have, starting at peak, going through 0, going through the midpoint, going to the negative maximum amplitude, going back through the midpoint, going to the positive maximum amplitude, going back through the midpoint, going to the negative maximum amplitude. I need to go a little bit further to get 2 whole cycles, and going back up to the top. Okay, so in this case, it's not sine omega t, it's not sine lots of how much we've displaced ourselves by, our angular displacement. It is instead a cosine omega t. So the sine comes from the fact we're starting at 0. The cosine comes from the fact we're starting at positive amplitude. Let's imagine we're starting at negative amplitude. I'll draw it on in red so we can imagine that situation. Then we're going to have an exact inverse of the first one. And so we'll end up with x is equal to minus a cosine omega t. Or, and you don't need to know this, but you could also spot that this has been moved forward by a phase difference. I've moved it forward by 1/2 of a wave. So therefore you could just add that to the omega t, which would move your wave along. Now you don't need to worry about that, you don't need to worry about phase differences, but that's what we could add inside of our cosine to actually show us this part here. But let's not worry too much about that, because what's really important is to see these two different situations. Sine omega t, if t is 0, x is 0. I'm sorry, I should have put this in here. So if t is 0 and x is plus the maximum amplitude, then we're going to end up with a cosine. And if t is 0 and x is the negative amplitude, then we're going to end up with a negative cosine. So the red one would be if t equals 0, then x equals negative amplitude. So hopefully you can see how this all starts to tie in to what we've been talking about so far. We've now got equations to work out the position, the displacement, relative to the maximum amplitude using the sine equation. We now understand why acceleration is proportional to the negative displacement, and that constant of proportionality is omega squared. And we've seen how that all comes together with looking at the components of those different situations and being able to work it out from there. So we've got two extra little bits that we just need to put at the bottom of this, because we're pretty much finished with the theory for this session. So let's imagine we weren't discussing our object on the turntable. We're instead discussing the pendulum. Well, it's mappable. That's the whole thing we've shown so far, is that what we've seen happen in circular motion is mappable to the pendulum. But when we're discussing the pendulum, so we're discussing the pendulum, not the circular motion, then what we're going to say is actually that x is varying from a negative sort of displacement r, which we'll call r, to a positive displacement r, positive r. So we can redefine a as r. So what we're saying there is if this is my pendulum and it's moving through like this, then actually what is changing is going to be, let's say that's positive r and that's negative r, and that's my midpoint there at the centre. So it's moving between those different points. But in this case, my amplitude is my maximum displacement from the centre point. Okay, so very similar about what we've been talking about, because if we turn this into a graph over time, again, we would see, well, in this case, let's draw it, why not? Let's have a bit of a practice with it. We're going to have time along the x-axis, we'll call it displacement x, and we're going to move from plus r to minus r. We're going to start at the positive r, so we're going to end up with a cosine curve. So if I wanted to work out x as a function of time, then I'm going to say x is equal to r cosine omega t. So that's the first sort of note to take away with this one. And the second note is remembering that displacement is x equals a cosine theta. That's ultimately what we're talking about, and the cosine theta came from the component of our displacement when we project it along one direction, when we're shining that light to project it in the same direction. And theta is the angle moved from the equilibrium. So in other words, if we're talking about our object that's moving around in circular motion, then obviously theta is going to be this angle that is moved from my equilibrium. In fact, that wouldn't be my equilibrium point, depends how we've defined it. But in fact, in this case, my theta would in fact be my angle moved from my equilibrium point there. So we are moving relative to the equilibrium point if there is the screen, because we're shining the light across that way, and my equilibrium point would be the end. So at time t, we can say that theta is going to be some point around this circle. And we know the whole circle is 2 pi, and we know we're going to go round the circle in a time period of t, so it's 2 pi t over t, because in some time t we're a relative position around that whole circle of 2 pi, and that's where we get our omega t from. So therefore we can say that the displacement is going to be a cosine omega t, where that omega t is in radians. So you must make sure your calculator is in the right version, so the right mode to get the answers for it. Okay, so that's the end of the theory.